Hi Math 30s, this is lesson 2 from your Counting Methods book. The title of it at the top says Permutations and Factorials. So you need to make sure that you've done the previous lesson, the fundamental counting principle. You'll see how it really ties into this lesson here. So at the top of the lesson page there, it says investigation. It says from a deck of 52 cards, choose 3 different cards. And to make it even easier, make sure they're different suits and different numbers. So if you have a pack of cards near you, Ace, I'm sure you do because you love cards, um, or you can just envision it in your head, um, pick 3 cards from it. So again, let's pick the Jack of Diamonds and the 8 of Hearts and the 3 of, I can't draw this, that's not the worst, 3 of Spades. Colored in black to make it look better. That doesn't look too bad. So choosing 3 different cards, it says, or using these 3 cards, fill in the chart before for how many different ways that you can arrange them. So this could be my arrangement 1. Then for arrangement 2, I could switch the places of the second ones. So I could have the 3 and the 8. And then for arrangement 3, I could now have something different at the beginning. So maybe I have the 3 here, the Jack here, the 8 here, and then I have the 3, the 8, and the Jack, and then maybe the 8 at the beginning. So what we see is if we are moving the cards around, um, in total, we get to 6 distinct or different arrangements of the cards. So we have 2 with the Jack in the first position, again switching the position of the 8 and the 3. We have 2 with the 3 in the first position, switching the position of the Jack and the 8. And we have 2 with 8 in the first position, switching the positions of the Jack and 3. So I just wrote 1, 2, 3 when I was doing it in my booklet. So we found 6 possible arrangements of the cards where they're all distinct, right? None of these are the same. So if I started here and I wrote 1, 2, 3, well, that's the same as our first arrangement. So that's not distinct. It's not different than what we've already found. Were each of your cards distinct or non-distinct? So this is what we're going to be discussing the next 2 days. So they're distinct and they're all different. So if you buy 2 packs of bicycle cards from the store, and the bicycle's kind of a brand, and they're both red cards with the same pattern on the back, and you pull out 2 8 of spades, you wouldn't be able to tell which came from which deck because they're identical, or what we would call non-distinct. So the ones that we chose there are distinct. They are all different. So it says, do you think it would make a difference if some of the cards were the same? So like I was saying before, if we had multiple decks of cards and we chose 2 Jacks of Diamonds and an 8, we can't tell if that arrangement and that arrangement is the same, because it would look the same, right? The cards are the same if we kind of shuffled it in our hands really quickly and we wouldn't be able to see which one moved around or didn't. We wouldn't be able to tell the difference between these 2 arrangements if they are even different. So the next one is, how could you have answered this question without building a table or without moving the cards around like we had it before? And the hint that it gives you there is think back to yesterday, so, or last day, whenever you did it. So if we use our fundamental counting principle, we know that there are 3 different options for where the cards can be. And the first card, it can be any of the 3 cards. The second card can't be the one that we put in the first position. We can't have that same card in 2 places. So there's only 2 options of what card can go there. And the third card has to be whatever the leftover is, so multiplied by 1. So that gets us to our 6 arrangements that we saw both with the table and now using our fundamental counting principle in order to figure it out. So now if I told you to try it with 6 distinct cards, so a jack, a queen, a king, an ace, a 2, and a 3, and make a table, you would get pretty irritated with me pretty quick because there's actually lots of different options. So this one, making a table, is going to take way, way, way too long. So you'd probably want to be using your fundamental counting principle. But if we have 6 cards, any of the 6 can be in the first position. Then after that, any of the remaining 5 can be in the second position. Then after that, any of the remaining 4 can be in the third, fourth, the fifth, the sixth. So there's actually 720 arrangements in an example where we have 6 different cards. So now it says, what if you had to arrange all 52 cards? Holy heck. Have fun punching that into your calculator. It takes a while, and if you mess up a number, it screws up everything. But that's saying that there are 1, 2, 3, 4, 5, 6. I'm not going to keep going, but you would have to draw out 52 positions. And again, there's any of 52 in the first. Whatever is in the first spot can't be in the second. So times 51 times 50, and so on and so on. And so we get 8.07 times 10 to the power of 67. So that is an 807. So we already have 2 numbers after the decimal. Sorry, I didn't want to actually draw that there. So we need 65 more zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those of you that are freaking out that I'm going to sit here and count to 65, I won't. But you can see that it's a ginormous number. So again, if you and your friends all say, arrange these 52 cards in any one order, there is basically 0 chance that any of you will organize it in the same way. Even if I gave you both, you and a friend, 6 cards, it's pretty unlikely that if I told you to organize it, that you would organize it in the same way. Yeah, I didn't realize that I just put all my notes in this. Usually I do this as you guys kind of do an investigation on your own and then we talk about it, but that's kind of weird. I don't know why I have a G here. That doesn't make sense. It says, in how many ways can the letters of the name Jim be arranged? So we can write it Jim or JMI, so switching the positions of the last 2 letters, or MIJ or MJI or IJM or IMJ. Same idea as the last question. So same idea. We have 3 objects, and so those are the letters that are different. So again, method 1 was just kind of make yourself a little sample space or table, or just write out what you have. And then method 2 is the fundamental counting principle. So in the first position, the first letter can be any of 3. The second letter can be any of the 2 remaining because it can't be whatever's in that first position. And the last letter can't be whatever's in the second position or whatever is in the first position. So it can only be 1. So 6 possible arrangements. Sorry, this is from the next portion. So on to this. So this is usually when I start teaching. You would have done the beginning part on your own. So an arrangement of distinct or different objects in a definite order is called a permutation. I'm going to put some big time underlines under definite order. In this unit, I'm going to ask you a lot, does order matter? And that's actually what you need to be asking yourself as well. So one can list all the possible arrangements, but we learned that we can determine the number of different arrangements using the fundamental counting principle. Oops. But this beginning part, so one can list all the possible arrangements, but we saw with that last one, so 6 cards, was 720 arrangements. That's too many for you to list. So you're probably going to want to use the fundamental counting principle quite often. So even sometimes the fundamental counting principle can be cumbersome to write. So that was our 52 cards one. So our 52 card one was a little bit cumbersome to write. I wasn't writing all those numbers. So to speed things up, we've discovered a new notation. Let's just pretend. There is a new notation that we're going to learn about called factorial notation. And it uses the symbol exclamation mark, which is my favorite. So sometimes we'll see something that says 5 factorial. And I know that you really want to yell 5 like as loud as you can because you're excited because there's an exclamation mark and there's never exclamation marks in math. But that's the factorial notation. So what that actually means. So the definition is the product of integers from 1 to n is called n factorial and denoted by n exclamation mark. So n factorial, this is probably easier to represent with numbers. 5 factorial, we'll just do this up here. So 5 factorial is actually equal to 5 times 4 times 3 times 2 times 1. 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. So what you see is when you have factorial notation, it's that number multiplied by one number less than that, multiplied by one number less than that, multiplied by one number less than that, all the way down to 1. So that might help us with this notation here. So n factorial, what that represents, n factorial represents whatever n is multiplied by 1 less than whatever n is, n minus 1, right? 1 less than n. So here n was 5. The next number is 1 less than 5 multiplied by n minus 2. And then that just keeps going on until we reach 3 times 2 times 1, right? That's how all of these factorials are going to end, 3 times 2 times 1. So whatever your number is here, you just keep counting down by ones until you get to times 3 times 2 times 1. Just as a note, n needs to be a natural number. So it can't be 0 and it can't be negative either. Yes, the other thing, I didn't really leave myself the appropriate amount of room. Sorry, I'm just looking through my notes if I actually have it tomorrow. Oh, I do. We'll talk about permutation notation in a little bit. So it says evaluate the following. So in your calculators, oh my gosh, I don't have one with me right now. In the TIs, you press second function math or just math. Oh, hang on, I'm gonna pause this. All right, I've got a TI. So Jax, you'll have to kind of look around, but you might be able to find it. Let's go back to here. So in order to find it, you press just the math button. Then you scroll over to PRB. It's talking about probability. So PRB, and then it's number 4. So in your calculator, what you would actually do is put in, again, you'd put in 10 and then press math and then scroll over, I think it's 3 to PRB. It's number 4 is the exclamation mark. Jax, I always mean to write this down and I did not. But there's probably on your menu screen something that might say PRB as well. if you can't find it and you can't figure out where it is, just let me know and I can get Corey too. I'm sure she has a Casio at home with her. I do not. So in your calculator, you can put it in as 10 factorial, or you could just put 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And so what you would get there, I probably would do this way instead, is 3,628,800. So the next one is 12 factorial divided by 10 factorial. So again, you can bop that into your calculator, just 12 factorial divided by 10 factorial. I just want to show you kind of an algebraic way that you can actually solve this out. So 12 factorial is 12 times 11 times 10 times 9 dot 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 times 3 times 2 times 1. This one, 10 factorial, is 10 times 9 times everything until you get to 3 times 2 times 1. So what you'll see is on the top we have 10 times 9 times 8 times 10, 7 times 6, blah, blah. And on the bottom we have that same thing. So what we can actually do is it's kind of like it's a factor of both. So we can cancel out the bottom, cancel out the top, and all that's left is 12 times 11. So 12 times 11 is 132. So again, you could have bopped that into your calculator and got to 132, or you can kind of look at it the algebraic way that 10 factorial is less, so the only thing that's going to remain is just 12 times 11. 12 factorial divided by 10 factorial times 3 factorial. So I know that this is kind of the same as we had before, so 12 factorial divided by 10 factorial. So I can change that part through this process to 12 times 11 divided by 3 factorial, because we know this 10 factorial is going to cancel out the rest of my 12 factorial, 10 downwards. 3 factorial is 3 times 2 times 1, 12 times 11. So I'm doing this kind of the algebraic way. Again, you can punch this all into your calculator, but the algebraic way. 3 factorial is 3 times 2 times 1, which is 6. So now I know I can take a 6 out of both the top and the bottom here. So again, I could rewrite 12 as 2 times 6, and then I have a factor of 6 on both. So now I have 2 times 11, which is equal to 22. So these are just different algebraic ways that you can solve these, but again, you can punch it in your calculator. This one is just if you punch it into your calculator, it's something that will come up later. If you punch in 0 factorial, that actually represents 1. So there is one way to organize 0 objects. There's not more than one way, and there's not 0 ways. There's one way to organize it. It's a little bit more complex than that, but just if you come across a 0 factorial, when you punch it into your calculator, you'll see that it's equal to 1. So the reason that I was showing you kind of these algebraic methods here is when you don't have numbers, like the next part. It says, simplify the following where the variable n is an element of the natural number system. So it is not, I guess, n needs to be greater than 0. But whole numbers greater than 0. So n factorial divided by n subtract 1 factorial. So n factorial we could rewrite, I did this on the last page, n factorial we could rewrite as n times n minus 1, put brackets around all of it, times n minus 2, all the way down to 3 times 2 times 1, depending on what n is. N minus 1 we could rewrite as n minus 1 times 1 less than that, right? Factorial 1 less than n minus 1 would actually be n minus 2, right? If we have n minus 1, subtract another one, that's n minus 2. And that would go all the way down to 3 times 2 times 1. So just like I had above when I had that 12 factorial divided by 10 factorial, we have this same factor, or same series of factors. divided by this. So we can just cancel that out. And so what we're left with is, sorry, n. So n factorial divided by n minus 1 factorial is equal to n. Sorry. So n plus 1 times, oh sorry, n plus 1 factorial divided by n minus 1 factorial. So n plus 1 factorial is n plus 1 multiplied by 1 less than that. So n plus 1 subtract 1, it's just going to be n. 1 less than that is going to be n minus 1. 1 less than that is going to be n minus 2. 3, 2, 1. In the denominator, n minus 1 factorial is n minus 1 multiplied by 1 less than that, n minus 2, right? 1 less than n minus 1 is n minus 2, dot, 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 times 3 times 2 times 1. And so now we see we have that same factor in the numerator and the denominator. So we can cancel that factor out and we'll be left with n plus 1 multiplied by n, which you could write it like this, or if you felt so inclined, n squared plus n. So that's using your distributive property to multiply out that binomial by a monomial. Oh, there's a couple more. Oh, yeah. I'm going to do question 4 first, because that might make a little more sense. It says, determine the number of arrangements that 6 students can form while lining up for Thursday lunch. And yes, I'm living in the past. There's no Thursday lunch right now unless I make it. There's nobody I can pay $5 to for a delicious meal. But let's just say there are 6 students waiting in line for Thursday lunch in the foods room. So how many ways can they be arranged? So we could pick the 6 kids in our class, kind of, and we could line us up and move us all around. We've already done one with 6, so you might also be thinking that. But so using our fundamental counting principle, 1, 2, 3, 4, 5, 6. So how many students can be in the first position? So the very first at the door, first to get the meal, whatever it is. There are 6 different kids that could be there. In the second position, well, the person who's in first is not also in second, so 5. Whoever is in first or second is not also in third, so 4 times 3 times 2 times 1. The other way you could write that is 6 factorial, which we did on the previous page, is 720. So there's 720 ways that those students could be standing in line. And order matters. Maybe this is a weird Thursday lunch. I'm going to write that actually. Order matters. So maybe it's a weird Thursday lunch where only the first 3 people get a bag of chips with their lunch and the next 3 get a rotten banana. So the order matters. If you're first, well, you're getting a bag of chips. If you're fourth, you're getting a rotten banana. So order matters in when we're talking about permutation questions, and we'll do a little bit more with permutation notation tomorrow. The other one, that's question 3, so just above that there, is saying solve this equation. So now we have an equation, so we have it equal to something. So it's saying n factorial divided by n minus 2 factorial is equal to 20. So what values for n would make that true? So you could do the old plug and chug where you'd be like, well, maybe n is equal to 6, so 6 factorial divided by 6 minus 2 factorial. So 6 factorial divided by 6 minus 2 factorial is 4 factorial. And so I would plug that out. So 6 factorial is 720. 4 factorial, 4 times 3 is 24. So no, that one's not going to work. But looking at it algebraically, let's look at the algebraic solution instead. So we could rewrite n factorial. I'm not going to do this again because it messed me up last time, as n times 1 less than that, n minus 1, times n minus 2, times n minus 3, all the way down to 3 times 2 times 1. We can write n subtract 2 factorial as n subtract 2 multiplied by 1 less than that, which is n subtract 3, and that would go all the way down to 3 times 2 times 1. So here we see we have the same factor of n minus 2 factorial in both my numerator and my denominator. I'm just going to write over here equals 20 because I don't want that to disappear. This is an equation. So now this and this can cancel out. So we're now left with n times n minus 1 is equal to 20. So now if you're thinking back even to rational expressions, sometimes we got to this point, something like this. We're going to use our distributive property because it doesn't quite help us. We want to collect everything on one side of the equation. So I need to multiply that out so I can collect everything on one side of the equation. So n squared minus n. I'm going to subtract 20 from this side and subtract 20 from this side. So this is me setting it equal to 0 at this point. We still haven't solved for n. I'm just going to put a box around it so I can see that. So n squared subtract n minus 20 is equal to 0. So we know when we have a quadratic, so you could use your quadratic formula to solve. You could do it graphically. So put it into your y equals button and solve for your zeros. You could potentially do it by factoring, which I'm going to do because it's right in front of me. So looking for two numbers that multiply to negative 20 and add to negative 1. So two numbers that multiply to negative 20 and add to negative 1. So again, if they multiply to a negative, that means one needs to be positive and one needs to be negative. And since the negative, it adds to a negative, that means that the bigger number needs to be negative. So you'd go through all your factors of 20, and it's going to be negative 5, positive 4. Maybe you box methoded something. That's cool too. So we can write this now as n plus 4, n minus 5 is equal to 0. And now we want to analyze what makes each of these factors equal to 0. So this would be n equals negative 4 and n equals positive 5. So, sorry, I'm getting texts from teachers all over the place. My phone's blowing up, guys. So we have two different situations, but if we look back up at the top, I didn't on this question, but I've said n needs to be a natural number. It can't be negative. So this can't be negative. So our solution is n is equal to 5. And we could always check that back in our question. So 5 factorial divided by 5 minus 2 factorial. So 5 factorial divided by 3 factorial. So again, you could punch this into your calculator, you could do it algebraically, you could write them all out and figure it out. But what it comes down to is it does equal 20, which is good because the left-hand side needs to be equal to the right-hand side of the equation. So that is it for the beginning of permutations. The next lesson is permutations as well. So depending on how you want to do things, if you feel like listening to me for one more set of times, you can, and then do all the questions a little bit later. Yeah, that's it. That's all. Thanks, guys.